Okay, let's keep going, shall we? So, again, multiple ways to find the mass flow rate depending on what properties we have and what we know. Okay, and this is what it represents: is the rate at which mass flows through this conduit, or any conduit, into or out of any control volume. Notice here I've got dots above m dot, so this is mass per unit time. That's what this dot is. This dot means this is energy per unit time. So if I have mass per unit time multiplied by energy per unit mass, that gives me energy per unit time. So again, common nomenclature is if I put a dot above a variable in this course and many other courses you're going to encounter. A dot above a variable means that variable is a rate. It's being measured per unit time. Okay, so it's going to be L3 and 4. This is page 1. Just keep me straight layer. Okay. Now, what else we got? Alright, so I've got here a slide here for example, time allowing. There is going to be time. Let's do examples kind of at the end. So the last couple of lectures here we'll just get about two or three examples done. Okay? Let's keep rocking along though. Let's introduce the first law of thermodynamics. And again, the whole goal of chapter 2 in the Chengel and Bowles text is to introduce to you the first law of thermodynamics. And then we'll do a little bit more. We'll talk more about properties, specifically about learning how to find internal energy and some other properties. And that'll be chapter 3, and then chapter 4, then chapters 4 and 5, we will really focus on using the first law of thermodynamics for just about any kind of system. As we mentioned last time, first law of thermodynamics is simply the conservation of energy principle. It's the idea that energy cannot be created nor destroyed, it can only change forms. Now, you've been introduced to this in a basic physics class, but you're really there looking at the conservation of mechanical energies. Mechanical energies being things like work, kinetic energy, and potential energy. It's easy to move those energies between each other. Here we're also going to consider the thermal energies, specifically heat and the internal energy. And we're going to include that with the conservation of energy that you learned about in physics class. Before I move here, what have I got? Okay, so I'm just going to derive this out on a sheet of paper. So the first law, let's just set this aside. You're welcome to follow along in the notes. I'm going to set it aside. And again, if we derive the first law, we talk about what is the first law. Well, the first law is saying energy cannot be created nor destroyed. It can only change forms. And so what we do is we say, well, that means the energy of a system, if the energy of a system changes, right, so that means we're going to go from a final state to an initial state. Now you can use F and I. That's probably what you use in a lot of physics texts. Here I'm just going to say, we're going to go between two states. So let's say state 2 is my final state, state 1 is my initial state. Okay? And what you have then is understand that the energy of a system, of course, at any state would be the internal energy, the kinetic energy, and the potential energy. Right, so these are the types of energy our system can have. And here we're saying, well, this is going to be the change in that energy. So delta E system is going to be all of these things at state 2. So it's going to be U2 plus KE2 plus PE2 minus all these things at state 1. U1 minus KE1 minus PE1. Right? Now, if we say M is constant, now it's true for a closed system, or it's not bad for certain types of control volumes, but if we say M is constant, that means it's the same M for each one of these states, at both states. So then we can say, well, delta E system, because this is M times, right, recall, big U is equal to M times little u, or little u is equal to big U divided by M, right? So if this is M times little u, so this is M U2 plus mv2 squared over 2 plus mgz2 minus all these things at state 1. mu1 minus mv1 squared over 2 plus, minus mgz1. Well, I've got the same m running throughout, so I can just factor that out. E delta system is equal to m times quantity u2 minus u1. I'm going to write it that way. Let's say delta u first. M times quantity u2 minus u1 plus v2 squared minus v1 squared over 2 plus g times quantity z2 minus z1. So these are all the types of energy that can change for my system, and if the mass is constant, it simplifies to this. Okay. Now, let's say also. If I look at the energy that comes into the system or goes out of the system, right? We say, well, what are the ways energy can come into or out of the system? Well, the ways energy can come into or out of the system, we said, well, there's work. We learned about that in our physics class. So I can have work going into the system, or I can have work going out of the system. I could also heat my system up. I could put heat in, or I could remove heat from the system, so I could have heat out. So heat and work, these are the two types of energy that cross the boundary for a closed system. Now, I might have a special type of control volume, well, any type of control volume. That mass is going to have its own energy. So the energy of any mass coming in or the energy of any mass going out has its own energy, and I have to account for that energy as well. So these are the types of energy that can come into or out of a system: work, heat, and mass. So all three of those can provide or remove energy from my system. Now here's the thing. Yes, Izzy, we're recording. Thank you for checking. The first law says that energy cannot be created nor destroyed. It can only change forms. And really what it's saying to us is that if I add all the energy coming in and I subtract all of the energy going out, that's going to equal the change in the energy for my system. Now, this is going to be a big, long equation. I apologize. It is what it is. Let's add up all the ways energy can come into the system. Well, that could be work, that could be heat, and that could be mass. So that's Wn plus Qn plus E mass in. Yes, Izzy, we're just fine. Thank you for checking on us. Minus work out, minus Q out, minus energy of any mass going out. So that's all the ins, subtract all the outs. And that equals the change. Well, what types of energy can change for the system? Well, again, if we assume the mass is constant, we can factor that out. And then we just track the internal energy change, the kinetic energy change, and the potential energy change. Now, you can think about this as this one big long equation, and you can try to memorize that, and some of you maybe have really good memories and you can do that. I don't. My memory is terrible. Engineering school has taught me a couple of things. One of those is be careful memorizing things if you're not going to use them every day, and you can look them up easily, or you can think about them another way. This is something you can think about another way. You don't have to memorize this one big long equation. If you'll think about it this way, think about it as in minus out equals change. This is easy to memorize, right? In minus out equals change. That's easy to memorize. This is kind of hard to memorize. Not impossible. I just would suggest most of you that's probably inefficient to try to memorize this. This is pretty easy to memorize. Think about what are the things that can come in, what are the things that can go out, and what are the things that can change. And then writing this equation becomes a little bit easier, right? So all the things that can come in are work, heat, and mass. And those are the same things that can go out. So in minus out. That equals the change. Well, what are the types of energy that can change the system? So it's a little easier to memorize if you break it down to its pieces and understand the system can have its own internal energy, its own kinetic energy, and its own potential energy. And we just need to track how those change. Really, Izzy? Are you serious right now? I'm sorry, guys. Again, in minus out equals change. And that's what we're after here. That's the first law. Now, here's the good news. Right? So this is in the notes, or in the PowerPoint slides, if you will. So here's the good news. Don't worry. We won't always use all these terms. In fact, we probably won't use all of these terms. It'll be pretty rare that we use all of these terms in one equation. And it's so big I don't even write it on one line in the PowerPoint. It's rare that we'll use all of these terms in one equation. One of our goals is to figure out which of these make sense for our system and which ones do not. Which one of these can I cross out as zeros? How many equations, right, on this one line right here, how many equations do I have? One equal sign, one equation. So how many unknowns can I solve for from this one equation? How many unknowns can I solve for from one equation? Oops, that's not a trick question. How many unknowns can I solve for from one equation? One unknown. So I can only solve for one unknown from this equation to solve a problem. So that means I either need to be able to have an equation to represent some of these other variables, or most likely I'm going to be able to say, well, let's say if it's a closed system, these go away, right? If I've got work in, but nothing really is pulling work out, then this is probably going to be zero. If I know it's losing heat, then I'm probably not gaining heat, or I'm not worried about the heat that it's gaining if I'm trying to find the heat out. So a common Chapter 4 problem would be, well, if I've got work in and heat out, what is the change in internal energy, assuming that these are zero? So, you know, Chapter 4 problem might be work in minus Q out is equal to M delta U, and that's it. And then we'll just have tools to find the other unknowns, but we'll get down to where it's manageable. Right? When I test you, when I put it on a test, I'm going to be testing on your ability to go from the most complex model down to the most simplified model that makes sense for your particular situation. And that's really what we're here to teach you. If you look at the learning objectives, I think number 3, the goal there is for you to be able to simplify something like this down to whatever makes sense for something you've never seen before. And that's our goal to teach you as engineers. Is I don't know what kind of systems you'll be designing as an engineer. If I've done my job right, they don't exist yet. You'll be building something new or designing something new, so I can't tell you how to do that. But what I will tell you is it's going to conserve energy. So you're going to have to figure out how to apply this to whatever it is that you build that doesn't exist yet. I hope that makes sense. Right? Yes, it's a challenge what we do. That's okay. We're engineers. All right. What else? Okay, that's all the slides I put in Lecture 3. Let's see what I've got for Lecture 4 real quick here. Alright, so Lecture 4, again, it's a summer class, so we got to do 2 lectures at a time. So let's talk about, you know what, I'm going to stop there. Let's call that good. I'm going to stop this video here, and we'll pick up on the next one. It's a nice stopping place. All right? So see you guys in a little bit.